Howdy. Howdy. Sounds good. Sound looks good. What the fuck? Sounds good. Sound looks good. Okay. I will stop looking at that. I will actually, let me bring that back up. I am streaming from home, and I gotta say, I'm not a huge fan of it. For some reason, the settings, or it's OBS. Both are OBS. Both are Linux boxes. Both are running the same Linux Mint kernel, but for some reason they don't behave in the same way. I don't know why. So I am going to ramble for a few 10 minutes. Oh, my OBS is over here, my camera's over here, so you probably will watch me look over there a few dozen times. So I'm gonna fiddle with things and then officially start at 10 when I said I would. So where is there? Oops, that's not what I wanted. I wanted to do that. And okay. Howdy, everyone who may or may not be watching this at this point. I am just getting things situated. Put this over here. Hey, howdy, Professor Phil. Still need to get you on Coffee and Science at some point. Just having some issues with OBS, so I am just fiddling. I'm going to start in about 4 minutes when I said I was going to. So let me see, where is this? Okay, let me bring this up. Hey, 3 PhDs in the house. Wonderful. Yeah, all right. How are you two fine gentlemen doing this morning? Or afternoon for one of you, and I think evening for the other. My squeaky chair. Either of you folks planning on watching the Artemis launch on Monday morning? Well, Monday morning Eastern Standard Time anyway, or daylight time, whatever time we're in. Is this a PhD only stream, isn't it? Well, I hope not. Not that I hope there's some other folks, and I've got the settings right. Yeah, I'm going to talk a little bit about the Artemis launch in a sec. Thanks. I don't know how many other folks are going to be joining us, but we'll see. PhD Rachel's in the house. How you doing, Rachel? About to start. I started early because of technical issues, but I'm going to start at 10. Although, I don't know, I'll just start now. All right. Howdy, all. Professor Parks, PhD here, and thank you for coming to Saturday Morning Science. This is the first episode, so you'll please have patience for me. I will eventually have a intro and outro for this stream prepared at some point, but considering it's the first week of the semester, I have my priorities are elsewhere at the moment. So what this show is about is what I wanted to do was show folks how astronomy is done, or at least how photometric astronomy is done, because that's typically the type of work that I do. But I wanted to put my own, put a different spin on it. I have two different streams, though they are both in the description. Links are in the description, where I've already sort of done this previously. But the difference here is I want to sort of restart this and frame it in terms of the scientific method. Because I have been accused, or it has been said, that science, or that astronomy rather, is not a science. And so while that may be a minority view, hopefully that's a minority view, I still think it is important for folks to see how the scientific process works, at least generally speaking. So we will be getting to that in a moment. Now, first thing that I want to do is I would like to thank Dora Naku. Really need confirmation on whether or not that's how you pronounce your last name, Dora. She became my first patron, as far as I know, my only patron at this point. But thank you very much. If you would like to become a patron of this channel, the link is in the description. Now, the reason why I bring this up is because all the money from my Patreon goes to helping these lovely bunch of knuckleheads. So what we're seeing here is Discord. This is the Discord channel for the Friends of the Observatory. This is a student-run organization here at George Mason. All of the funds, or all of the proceeds from my Patreon, go to essentially them, and to also fund other outreach projects. This was last night. This was the first this was a freshman only, as far as I know, group meeting. And you can see some of our students here. We have a 16-inch Dobsonian, which we have named the Plavchan, which after the director of the observatory. We also have our smaller, just refracting telescope. I really, really would love to replace that with a Takahashi at some point, but, dreams. Whoops, that's not what I wanted to do. Although I guess that works. Here's another. Again, as far as I know, these are all freshmen, or primarily freshmen. Here is again our 32-inch dome. If you are new to the channel or unfamiliar with what I work with, I work at the George Mason Observatory. That is the dome for the 32-inch telescope. And so these these nice students are getting introduced to it. Just some more pictures. This is our control room where we can this was our control room before we got a handle on actually doing this stuff remote. But we still use it as primarily for safeguarding, obviously, and for public events such as this one. Some more. I'm very proud to show these pictures because I am very impressed with our student organization and how well organized it is and how well it's advertised. Because this is my 5th institution that I've either been a faculty at or a student at, and this is by far the most active astronomy club I've ever encountered. So I am very pleased when they do with this sort of thing. And the last thing I'm going to show is, well, let's do that. This is our solar telescope. It is 150 millimeters, and it is a specially designed telescope to filter out most of the light of the sun. These are two of our photo members. This is our secretary, if I'm not mistaken, Emmy, and this is Patrick, if I know who I'm talking about. He's actually one of our new graduate teaching assistants. He was an undergraduate at GMU and was a tour guide, and now he's been promoted. Well, and that's one of our robots that we have on campus that delivers food for us. That it will eventually, there'll be an uprising and they will eventually take over campus, much to everyone's chagrin. So but the last thing I want to show you is this. Aha. Now, I don't know if this was intentional. I suspect it was. This is an image of the sun that has been taken so that the sun is not quite fully centered, so that it can you can see this feature, which if I was going to say that it was a prominence, but considering its structure, I would say that it's actually a flare, which considering how the lifetime of flares, that's actually rather serendipitous find for them to see. And so very happy with that, basically kind of like a proud parent when it comes to these kids. So let me bring the chat back up. Now, for those of you who aren't aware, we are, let me actually just bring it up. There's kind of an important mission going on soon. And that is the Artemis 1 project. And this is the NASA's continuation of our lunar program. Obviously, we had the Apollo missions; those ended about the early '70s, if memory serves. And for a variety of different reasons, we shut down the continuation of that program. NASA had dreams of creating or orbital base. Why am I losing that word? A space station in orbit, which would then be followed up by permanent installations on the moon. That all got sidetracked, like I said, for various reasons, probably budgetary, if I had to make any kind of educated guess. After years and years, and probably a whole lot of bugging from the FE community, I'm kidding, NASA decided we are going back. And the Artemis 1 mission is essentially a proof of concept. It's a mission that's going to launch a vehicle towards the vehicle to the moon, orbit the moon, and come back. This is in preparation for actually sending people again to the surface of the moon. This is going to be launched, weather permitting, Monday morning, and I think it is at 8:45 Eastern Standard Time. I apologize, I did not convert that into UTC, but I'm sure you can easily Google the specific time if I'm wrong. But it's certainly going to happen on Monday morning. I had plans on doing a watch party or streaming something, but fortunately for you all, I guess, but good for me, I actually got invited to a launch party hosted by Google, and so I will be rubbing elbows with folks and basically begging for money for GMU and our outreach program. So that hopefully will be a blast, pun intended. Aurigae says, I want to know why launch to orbit the moon has been done. If it's been done before, I don't see the point. The point is that while it has been done before, it has not been done with this technology. And so this is the vehicle that they plan on, as far as my understanding is, this is the vehicle they plan on taking actually living folks to the moon. So they want to be able to, they want to make sure that the technology that we have currently can actually accomplish that without any sort of catastrophic failures. So that would be the point. Yes, Professor Phil Bill is correct. NASA is looking for a permanent station on the moon, and I made the jest that it was prompted by the flat Earth community, but in fact, my cynicism tells me that it was prompted by a burgeoning space race that really no one is talking about between us and China, and possibly the Russians. Although there have been a report that the Russians reported themselves that they were going to actually divorce themselves from the ISS. However, if you look at the specifics of the situation, that's not going to get done anytime soon, assuming the Russians want to actually keep a presence in orbit. Right now, the Roscos, the Russian space agency, really doesn't have the capacity to put a space station in orbit. That proposal is still in the preliminary phase. And while the Russians did say that they were going to leave, they didn't really put a time frame on that. So I think that was just a bit of saber rattling. We'll see how that goes. But yes, there is, in my view, there is in fact a space race going on that is getting very little attention for reasons that I don't quite understand. All right. But that is a topic for a different time. I might even actually create a stream solely based on Artemis. Maybe next week I might do that. That sounds like a good idea. Talk about the Artemis program, the Artemis project, what NASA's intentions are, and also talk a little bit more about that space race that I alluded to. But I think that's all I wanted to say on that. Now let's talk about what the data that I'm doing, or the research project that I'm trying to finally finish. This was data taken, or this project involves data that I took all the way back in 2002. So 20 years ago, I took this data. So again, you'll please have to forgive me. This was one of the first serious photometric data runs that I actually made. So there are a lot of things that I would have gone back and actually corrected. A lot of these images, if I knew then what I know now, they would have been taken differently. So, but this This data was taken from Emory University when I was an instructor there. And I will see if I can show you an image of it. Observatory, I can spell. This is a bit, here's the back end of it. This is a bit dated. Let's see what we got here. Let's see if I can show you an outside view of it. This is the telescope. That is the DFM telescope that we use, the outside of it anyway. It is a DFM. I have to admit that it is, DFM makes a real nice telescope. There are three manufacturers of telescope. I know I'm digressing a little bit, but there are three major designs of telescopes, or manufacturers of telescopes. There is DFM, there's plane wave, and then there's optical guidance systems. If I were to rate them in terms of quality, and I've used all three, if I had to rate them in terms of quality, I would say DFM is Mercedes level, just very, very nice telescope to use. Plane wave is, let's say, Cadillac? Cadillac. And then OGS, we're going to say, Honda. All of these are great telescopes, but those would be the ones I put in order of preference if I were given money to do it, and money to purchase them. That is also the order in decreasing cost of those telescopes. Again, DFM being the highest and OGS being the lowest. So this data was taken using this 24-inch telescope that you can see here over to the right. It was used. I used an AP4 or Apogee camera with 5 different filters: U, B, V, R, and I, which correspond to an ultraviolet filter, or a light that only is, or the majority of which is in the ultraviolet range. B is blue. The light that passes through the blue filter is, majority of that is blue, if not all of it. V actually stands for visual, but really what it means is green. R is red, and I is infrared, where most of that is actually in the very, very near infrared part of the spectrum. Professor Philbill asks, how much money roughly? For which one? DFM? I'll just tell you all three. So, as far as I can think of it, I know the DFM, that particular telescope, again, it's 24 inches in aperture. That one in 2002 cost $250,000. Plane wave, or OGS, the one we have at GMU, from my understanding, it's obviously a 32-inch aperture, but from my understanding, it costs in the neighborhood of a couple, like 10, 20 grand, somewhere in that range. And then plane wave is, I think, low 6 figures, if I had to make a guess. So yeah, the Mercedes, that telescope is $250,000. If you want it in meter size, which they do make, 36 inch, that'll only cost you $1 million. And the reason why I know that is because after they installed this, I asked them what their next plan was, and they said, oh, we're going to be installing a 36-inch telescope in North Georgia, and that one is for a private observatory owned by or being built for a dentist. And yeah, they told me that it was going to be $1 million to build that damn thing. Like, I went into the wrong business. Anyway, the camera that I used was an AP4. At the time, it was a 1 megapixel. I want to say crud. File size is about half a gig for each. No, I want to say 1 megapixel. Never mind. 1 megapixel camera. Again, it was 2002, so best we got. Now, why did I do all this? So in 2000, when I was there, I decided that I got my master's in 2000, and so after a couple of years, I was like, all right, I want to get back into actually doing research. So what kind of research can I do using a 24-inch telescope with that AP4 camera in Decatur, Georgia, which, if you know anything about the geography of North Georgia, which, given my audience, you probably don't. It's a suburb of Atlanta, Georgia. So what I'm trying to say is, it ain't the darkest of skies. So what can I do with this? Well, it occurred to me that what I could do was, in fact, look at binary stars. Now, what is a binary star? A binary star is two stars that are gravitationally bound to each other. And they come in a variety of different flavors. Let's see if I can do this. Let's go to ye olde Wikipedia and see if they have so what were they do? Okay, this is actually, that is what I wanted. So I'm going to look at, so binary stars come in, like I said, different flavors. There are visual binaries, there are eclipsing binaries, spectroscopic binaries, and so forth. What I'm specifically going to be looking at is eclipsing binaries. Now, those are pretty easy to find simply because nature is social. When we look at, from an astronomical point of view, when we look at objects, any classification of objects, you're almost certainly going to find those objects in close vicinity to other objects of like kind. Asteroids. Find one asteroid, you're probably going to find a whole lot of them. Planets tend to come in families. Stars also tend to come in groups. Over about 50% of all stars in the universe are binary, at least binary. They may be quadruple systems or triple systems, quadruple systems, or even larger. So binary stars are pretty, I wouldn't say ubiquitous, but they're very, very common. We're going to be looking at an eclipsing binary. Now, what an eclipsing binary is where one star passes in front of the other and causes the light to diminish over a certain period of time. And here we have, the case is we have a large primary component and a smaller secondary component. What I mean by primary and secondary is where, no, actually I got that flipped. The smaller star, which is the brighter star, the brighter star is the primary component. Most of the luminosity of the system, the total luminosity of the system, comes from that yellow star. Even though it's smaller, it's hotter, and so it's considered the primary component. The larger star, the redder star, the more evolved star, is the secondary component. And so when we look at this, what we're seeing is when you look at the star when it's just doing its thing, you're going to see the star as a single object. Well, actually, at any point, you're going to see the star as a single object. You will not be able to resolve the two stars separated from each other. The telescope does not have the angular resolution in order to resolve those two out as a pair. But because they are very luminous, we can still see them. They may not be fully resolved, but we can actually see them. When they are separated, like you can see on the screen, you have a certain maximum brightness of that system. Basically, you're getting the luminosity from both objects, or both stars. But because of the way the orbit works, one star, the primary, is going to pass behind the secondary, and the brightness is going to diminish by a certain amount depending on the physical characteristics of both objects, primarily the temperature difference between the two. And the reason why the brightness drops off, and hopefully it's fairly obvious, the reason why the brightness drops off is because the brighter of the two objects basically gets blocked out. It disappears from view. And that happens for a certain length of time. It reappears from the backside. That is known as a primary eclipse. This over here is when the primary passes in front. The primary component passes in front. This gives you a secondary eclipse. The reason for that is because the hotter or the bigger star is cooler. When part of it gets blocked out, there is less light being blocked out than when the hotter star gets completely eclipsed. And so again, you have a small diminution of light. Now this is what we call a light curve, and this is ultimately what I'm going to be trying to extract, because the light curve can give you lots of different information. It can give you information on the temperatures of the stars, on its luminosity, temperatures of the stars, the radii of the stars, and so forth and so on. But there are also, when you also look at binaries, there's another type of, there's another sort of classification that you need to consider. We have basically three, or really four scenarios. You have detached, meaning that the two stars are well separated, and because of that, the gravitational attraction of one onto the other does not distort the physical shape of the two. In more technical terms, if you were to look at this line here corresponds to an equipotential. Basically, if there is a particle of matter on that equipotential, it can basically just, any sort of perturbation is going to send it anywhere it wants to. At that point, the material is free to escape out into space. These are known as the Roche lobes. And you can see that they're teardrop shaped because of the fact that you have the gravitational influence of one onto the other. If you were simply looking at a single star, that equipotential would be a sphere around that star. But because of the binary, because of the proximity of the other star, the Roche lobe is, in fact, distorted in that teardrop shape. So this is a detached system. This is what we would call a semi-detached system, where the larger star, in fact, actually fills its Roche lobe. So it is very unstable in terms of holding on to its own mass. And then you have, this is actually overcontact. A contact binary is actually when both stars completely fill their Roche lobes, and that's it. This is an overcontact binary, and it's a fascinating object because, technically speaking, while these are two different stars, they share a common atmosphere or a common envelope. Now, the reason why I point this out is because I am going to be looking, HL Aurigae is in fact an overcontact binary. One of the reasons why I chose it was because of the fact that overcontact binaries, because they are so close to each other, Kepler tells us that their rotation period or orbital periods are very, very short, on the order of hours to days, or tens of hours to days. And so I really wanted to get, I wanted to get data, impressive looking data, as quickly as possible. So I was essentially impatient when I got there. Now, one of the consequences of, now you might be asking, Rob, why look at these binaries? Well, aside from the fact that you can, by looking at getting these light curves, you can tell physical characteristics of these stars, their radii and their temperatures, two fundamental properties of a star that are difficult to determine directly any other way. Not impossible, but difficult in any other way. But why did I choose an overcontact binary, aside from the fact that it's observationally inexpensive? Well, that is because what I was really curious about are star spots. Now let's see what Wikipedia has to say on star spots. Oh, real quick. This image, a friend of mine, actually my boss when I was a postdoc, Dr. Fabian Baron, this is Algol. This is awesome in that this is a direct image. Now, this star, the primary star, is fully resolved. So it looks basically like a sphere. Now the blobby thing that is surrounding the companion that's going around is only partially resolved, hence why it looks blobby rather than a sphere. But you can see in essentially real time, well, this is sped up, but you can see this object. We have direct images of one star passing in front and passing behind the other. This was one of the first binary systems where both objects were resolvable using interferometry. So, yeah, just name dropping there. I know that guy. He was my boss. Star spot. All right. Well, let me just Google it. Aha, well, kind of. The orbital period of HL Aurigae, I have to admit, the orbital period of Algol. You know what? Let's look that up. I want to say it's 7 days, but I might be getting that confused with Beta Aurigae. Or, yes, Beta Lyra, sorry. Algol period. Oh no, the period is actually much less than that. It is 2.87 days. Algol, just a little bit of trivia for you. Algol or Algul translates to the demon in Arabic, and one of the reasons or motivations behind why they called it that is because it visibly changes in the night sky. If you know where Algol is, and you're in a fairly decently dark sky, this is a magnitude range of about 2.1 to 3.4. That is roughly a brightness difference of about, I want to say, 3 times. So the star changes in brightness by a factor of 3 over the course of roughly 3 days. So this was obvious. It's obvious now, and it was certainly obvious to the ancients, or to Arabic astronomers and really Greek astronomers, and they referred to it as Algul because essentially they thought of it as a demon eye winking at them. So this is something that if you are interested in, you can go out and actually see this for yourself. If you just either naked eye or use a pair of binoculars and just go out, spend a few hours each consecutive night, you will see that that star, in comparison to the stars around it, actually does vary in brightness. Now, let's look at this from as I said before, I wanted to look at this from a scientific, what am I looking at here? Scientific method. Oh, yeah. Yes, I know her. Oh, I guess I'm not on campus, so I can't actually access that article. So let's just go back to this. So what we find is if we look at H.R. Aurigae, so the scientific method basically starts with seeing something, either measuring, having a measurement, basically a fact. It starts with a fact, a measurement or an observation of a phenomenon. You then basically research that fact to find out why exactly it's doing what it's doing. And so H.L. Aurigae has been known to have these periodic dips in brightness. So if we look up H.L. Aurigae from a actually, no, there's a better way to do this. So if I were an astronomer and I wanted information on a star so that I could look it up and find out what have other people done on this particular object, I would use a service called Simbad. And here's the URL. Whoops. Yeah, you can see it. Here's the URL for it. Basically, you can punch it in. There are a number of ways that you can search for stuff. This identifier, we're going to call it H.L. Aurigae. There we go. Got it. We got an Eclipsing Binary. We have a utility that allows us to figure out where it is in the night sky if you don't already know. It gives you the coordinates. It gives you the magnitudes, the mean magnitudes of these things. It also tells you how far away it is. But more importantly, you can look up references. And so there are 56 references or 56 papers that H.L. Aurigae has been mentioned in, either as the sole object of, or the sole focus of research, or as just a survey of eclipsing binaries. So let's look at this. Let's try to find one. Let's try to find one with actually H.L. Aurigae in it. Okay, no astronomy. Oh, that's right. I can't. Can I get the paper? I should be able to get the paper. And so we see here that there's been this particular study is looking at a pre-contact binary system with a solar mass companion. And this is the analysis, or the work that's been done here is using CCD and photoelectric minimums, or photoelectric data. And you can see that it has a, where is the actual, oh, this is actually saying that it's got a third component. I apparently need to look this up, look more into this. Interesting. All right. But the point I'm trying to make here is that you can use Simbad to research this object and find out what else has been done with H.L. Aurigae, and then go from there. Another nifty thing that you can use is, can I not display those anymore? Is that certain measurements also have been cataloged. And so here, what we find is that these are the published variations in brightness for this particular object. Again, we see that as one star passes in front of the other, the light is going to diminish. And what we see here is that the light varies from 10.6 magnitude, which is magnitudes are inverted, 10.6 magnitude down to 11.3 magnitudes. Each magnitude difference is 2.5 times in brightness. So a magnitude 10 star is 2.5 times brighter than a magnitude 11 star. And we also see that the period of this object has been measured to be about 0.622506 days. So again, very, very fast. So we know that this is binary, but on top of that, we notice that there are peculiarities about the light curve. So the light curve, if it were just two stars, the light curve would have a definitive shape to it, and that shape would be constant over all time. With HL Aurigae, what I was able to find was that HL Aurigae's light curve is a little wonky in that it doesn't have that regular sort of appearance. There is certain deformations in that light curve that cannot be explained via the eclipsing mechanism alone. And so the question becomes, could these objects, or could this deformation be created by star spots on the surface? So this is actually not a great image. Let's try that one. Oh, look! That's mine! I did that. Anyway. What we're seeing here is a projected image of the sphere of the star, and these dark spots are in fact star spots. And so the idea is, as these spots come into view and leave the view, that modulates the brightness, causes the brightness to go up and down, in addition to the modulation due to the eclipsing binary itself. One star passing in front of the other. So, and that's what I'm really interested in. I want to know, does this variability mean that there are star spots on the surface? And if so, can I say anything about them? Actually, it makes sense. There you go, science. Glad this is making sense. I feel like I'm babbling a little bit. So, that's my... I saw that HL Aurigae varies in brightness. I did research on it, found out that it was an eclipsing binary, but I also found out that it has possible evidence, or it has a weird light curve that could potentially show us that, or might indicate evidence of star spots on its surface. Which, the implications of why would I want to know this? Why am I curious about this? The reason for that is because star spots are a symptom, I guess, or a consequence of a star's magnetic field. And I had this grand sort of research goal in mind when I was a wee grad student, where I wanted to know what the magnetic field of a star does, or how it evolves from its pre-main sequence phase, where the star is exceedingly active, spots all over the thing, through the main sequence phase, like the sun, where the spots are not so impressive in relation, to to evolved stars like you find in HL Aurigae, which have spots that are almost the size of, they're ginormous, and they have many other different characteristics that are just not solar in any way. And what that tells us is that the mechanism behind which the magnetic field is generated is not the same. And so by probing these sunspots, by getting data on these sunspots at various intervals of stellar age, I can then feed that to the theorists, and they can tell me why it's doing that. So that's ultimately the reason behind all that. All right, what do got here? Who's wrong? Witsit just put out a video where he claims the scientific method isn't required in every instance. What are your thoughts? Yeah, okay. Whatever. Glad to see Witsit's keeping himself out of jail. That's all I gotta really say on that. Let's see. He's wrong. It's required for science. As Feynman says, if it disagrees with experiment, it's wrong. That's the key to science. No experiment, no key to science, aka no science. There is a great video by, the only thing that I will really add to that, or really say on that, is there is a great video by AB Science where he, in more detail, describes the fact that the scientific method, in particular, varies depending on what science you're talking about. The scientific method, in practice rather, is far different, or not far. The scientific method in practice is different for physicists than it is for biologists, than it is for psychologists. Depending on how you are able to interact with your field of study or your object of study, you have to tailor your experimental designs accordingly. Obviously, in softer sciences, I hate using that term, but in more social sciences like psychology or sociology, you really can't tinker around with somebody's brain. You can't open up their skull and start poking stuff. Although I guess you could, but that usually ends in bad things. So you're left with simply study or simply surveys and things of that nature, more subjective forms of experimentation, whereas physics is much more rigorous. You can actually manipulate the thing that you're looking at, or at least in principle. So, but yeah, so I'm plugging AB Science. He has, like I said, he has a lovely video talking about the scientific method and the various ways that it's different depending on what field of study you're actually in, what field of science you're actually in. So, all right, this is going to get, now we're going to get a little kludgy in that I'm really unorganized, but let's do this. So, so next step in the scientific method, I have the fact, the research, the question, what is my experimental design? How am I going to test this? Or how am I going to answer the question, do these stars have spots? Well, speaking of how how science changes depending on how you interact with your subject, as it were, obviously astronomy is a observational science. I cannot go out to HL Aurigae as much as I would love to and actually physically manipulate these things. I am left with only being able to observe the light from this object and then analyzing that light after the fact. So, what I need to do is I need to arrange an observation strategy that allows me to answer the question I'm looking for. Essentially, I need a light curve. I need a light curve that I can believe, and I need a light curve that shows, that potentially illustrates a presence of star spots. I know from previous research that the period of the star is around 0.622 days. So, if I had more experience under my belt when I was doing this project, what I would have done would have been to actually plot out what the light curve would look like in the future, and then chosen days or nights to fill in that light curve. So say on day one or night one, I know that it's going to be near maximum brightness. And I know that it's going to go through maybe 30%, I'm just making numbers up at this point, 30% of its rotational phase at that point. What I want, and what I mean by rotational phase, is a 100% phase or a 360 degree phase is at the starting point, it goes up, it comes down, it goes back up. Basically it completes, well, let's actually use the picture that I showed you before, where it's stable or it's nominal, drops, comes back up, drops again, comes back up. That's one cycle of the light curve. So I want to be able to sample that light curve very, very well, and very, very precise, or very, very well, and with a high what we call cadence. What cadence means is the time between observations. So a cadence of one day, is a rather gross cadence, particularly for this object. Because if you're looking at this, you're looking at HL Aurigae, which has a period of 0.622 days, looking at it every day is actually too slow. If you did that, it would take forever to actually sample the entire light curve, to actually get enough data to see the light curve in toto. So you have to choose your cadence, or how often you look at it, very carefully. I decided I'm going to look at it as quickly as I possibly can. I am going to basically take observations as soon as the telescope or the camera will essentially let me, and I'll explain that in a moment. So getting back to how I would observe this, I would have predicted what the light was going to look like with time, and carefully planned out when I was going to look at this star, so that I could efficiently cover all the shapes or all the points in that light curve. But I didn't do that. I was just basically, I'm going to sit at the telescope all night. As long as I got good weather, I'm going to just shoot the hell out of this. And what I was talking about in terms of as fast as I can, here's an image of, let's take, no, let's not do that. Let's go down here. Wait a minute, where are you? So many windows. There we go. This is an example of a raw raw image of the night sky, or of HL Aurigae. Now, I could use that tool before on Sinbad, and I can basically the sky chart, and I can determine that HL Aurigae is that one right there. This is a known star, a star of known brightness, and then these two are what I'm going to be using as my check stars. Now, what do I mean? Going back to as fast as I can. Well, what I need to do is I need to plot out my exposures, how long I actually take data, so that I get enough signal above the background in order so that that signal gives me good quality data. Another way of looking at it is signal to noise. How much signal do I have to the background noise around it? Now, there is no hard and fast rule to what signal to noise is acceptable. I don't like going under 10. I really like not going under 100. And so what I needed to do, I needed to figure out how long I needed to expose these things, or these images, or this star, so that my signal to noise was acceptable, above 10. So that the brightness of this star was basically 10 times the brightness of the background field or the background sky. And so I fiddled with that. made some observations with that. The longer you expose, the more light you get, the better your signal to noise. Briefly, it scales as a square root of noise, excuse me, it scales as a square root of signal. So increasing the exposure by 1 increases the. No, I'm not going to do that. I can't. I'm afraid I might say something inaccurate there. But it scales as a square root of signal. Yeah. Next time I will actually I will plan ahead and I will have a more coherent example of what the hell that means. Anyway, so this is my image. So I have to, like I said, I have to plan observations out. And what this ultimately meant was in the visible filter, or the green part of the image, this image, I needed 3 seconds. I needed to image this thing for 3 seconds. And I did this for each of the different filters, U, B, V, R, and I. I figured out how long I could expose these things and so that I could get the signal that I want. And that basically dictated my cadence, how quickly I could go from one object to the next. Now, filters. Why did I choose the filters that I did? Well, again, mainly because they were there, and I wanted as much data as I possibly could. What the filters tell us is it gives us an indication, essentially, of temperature. Looking at the ratio or the difference between the brightness in 2 different filters, like a common one is B minus V. If you look at the magnitude, the B magnitude or the blue magnitude, blue brightness of a star, and compare it to its green brightness, that is a proxy for how hot it is. If it's hotter, if the star is hotter, it's going to be bluer, so that difference is going to actually be negative because magnitudes are flipped. If it's redder, then that difference is going to be more positive. So it's used as a method of determining temperature. I'm going to be using that in a program that will allow me to model what these stars actually look like given the data that I have. And I'm going to talk more about that later when we get to that point. But for right now, what I want to emphasize is basically the reason or the motivation behind why I chose all 5 filters is I want to get as much data as I possibly can. As it turns out, I probably could have skipped using U because the data quality in the U filter ain't so great. But we'll get into identifying bad data and so forth later on. Let me check let's see. Let's see. Talking about, of course, the conversation's been talking about IV and DV. Now, I'm just going to read through here. Empirical data to establish a law. Suppose you want to. All right. So let me see. Let me use. I guess I can go into it now. How do we actually? Let's address the problem or let's address the issue of an independent and dependent variable. This has sometimes been this has sometimes been thought of as a very rigorous or dogmatic approach to the scientific method. That if you do not have an independent variable and a dependent variable, it's not science, because that is what tells you the effect or the cause of the effect that you're seeing. And in a certain way, in basic way, that's true. But at least from an astronomy point of view, I can't say anything about physics because I'm not a physicist, but from an astronomy point of view, we don't think of it in that terms. We do, but we don't. What do I mean by that? So let's take what we're going to be doing here. We have a set of observables. We have the brightness of an object over different colors over time, separated out by color or wavelength over time. What I'm going to do is once I get that data to the point that I extract all of that data, I'm happy with the data quality that I've got, what I'm going to do is I'm going to ultimately put that into a computer code called Phoebe. Now, modern astronomy is done in the following way. Well, one way of doing astronomy is done in the following way. What I want to know is, obviously, I want to know what is the cause that is causing the effect of the observable. So the observable is the effect. That the light curve is the effect. What is causing that light curve? So I punch that data into a model. And when astronomers do this, they use a model. They use a construct. And I know what flat earthers are going to say about that, but let me explain. Yes, it is not perfect. Obviously, there are going to be certain things in that model which we don't account for. But it is as best a representation of reality as we can possibly get. So in this particular case, the model is going to be of two stars that share a common envelope. And there are a number of different variables that we can vary. And honestly, I don't think about independent and dependent variables so much because I don't even know which one's which. All I know is that one of them, if you vary it, it actually affects the other. I think if the independent variable is one you flip, and the dependent variable is the one that that gets flipped because of that. Anyway. So this model is going to have certain parameters to it. It's going to have parameters like the rotation rate of the orbital period of the star, or orbital period of the system. It's going to have the sizes, the radii of the two stars. It's going to have the temperature of the difference between the two stars. It's going to have something called the limb darkening coefficient between the two stars. Essentially, the brightness of the star varies as you go from the center of it to the edges, at least when you observe it in this way. Then you have that's the bulk. That's really the bulk properties of the binary: the orbital period, the radii, the temperatures, and the limb darkening. On top of that, I'm going to be looking for spots. There, the model is, you add on top of that, you have the number of spots that you want to model, the location of the spot you want to model, and the temperature of the spot you want to model. Now, that's a lot of independent variables. Those are the independent variables of the experiment. The dependent variable, like I said, is the light curve. And that's what we're comparing. So I have basically the true values. I have what is observed. I have how the light acts as a function of wavelength, as a function of time. What I do with this model is I create this model using those different parameters. I put in, say, that the temperature difference between the two stars is 1,000 Kelvin. I put in that the orbital period is 0.622 days. Limb darkening coefficients are such and such. And then I basically create the observables from that. What the model does is it says that, all right, you have these two stars. These are, and this is the characteristics you gave it. If you were to observe it with the same observing strategy that you observed HL Aurigae, this is the light curve you would see. And I then compare that light curve that the model tells me or predicts, and I compare it to my observable. If they match, groovy. If they don't, not so groovy. I've got to change those variables so that the light curve essentially matches. And that's ultimately what's happening, is you're changing, the model will change the various temperatures, various temperatures, spot locations, things of that age, all the things that I was talking about before. And and the data analysis process, you'll run through all of that, and you'll just continually generate model light curves, and you'll compare those model light curves with the observed light curve. Now, this is where the strength of the analysis comes from. This is where where as a scientist, if I were to look at my own research, as a scientist, when I'm doing this research, I have to take certain things into consideration. And as someone who is critical of science, of someone else's work, I have to understand these considerations, and I have to see whether or not the author of that experiment also understands the considerations. So there are a variety of different ways that you can compare the similarity of the model light curves to the observed light curves. There are a number of different ways you can do it. There are pros and cons to to each one. A straightforward approach is called chi-squared. Is chi-squared analysis. Again, I don't know how far into the weeds I'm going to get when we get down there, but what chi-squared does is it talks about the difference between the difference between the model data point and the light curve data point. There are various ways so you have chi-squared as a way of determining how the two are similar to each other. Now, how do you manipulate the variables in order to get the chi-squared so that down to where the two light curves are the same, or basically the two light curves match? There are even more ways to do that. You can do the really slow way, which is to hold all of them fixed except one, and then change that and get as close to the observed light curve as you possibly can. That is the most akin to having one independent variable and one dependent variable. But that's real slow, and there are certain other headaches that go along with it. Mainly, it's just real slow. There are mathematical techniques that you can use, such as a downward simplex method or a genetic algorithm that allows for the manipulation of the changing of multiple variables at once. And essentially, by doing so, you can speed up the process greatly. So chi-squared is one way. Bayesian statistics is now basically the sexy person you take to the bar. Everyone does the Bayesian statistics at this point. Let's see. Let's see. They did the same thing in psychology. Work on the big five personality factors. Oh yeah. Blue says Clive science isn't always a guy in a lab coat pouring different colored goo from one beaker to the other. That is true. I have never worn a lab coat. I am never going to wear a lab coat. I am getting into ties though. Those are nice. Rachie, sorry, my bad, Professor Parks. Blue makes a good point. Clive's is still IV and DV though, but I concede to Blue's point and I understand your point about many variables having effects. Phil Bell says, blue, that's why I decided to do chemistry when I started. It didn't take long before the machines took all the fun out of it. So yes. So Rachel, I hope that was clear enough. And again, if you were to watch this series further on, when I actually start doing the data analysis, I can show you actual examples of what I'm talking about, where you take a program and depending on what program you're using, it's going to use a different technique, but it's going to use a certain mathematical technique to vary these different variables, temperature, orbital period, so forth and so on. It's going to vary those parameters. It's going to then spit out a predicted light curve, and then you compare that predicted light curve to your observed light curve, see how well they match, and you just iteratively go through that process until you can't improve that match anymore. Now, there's an important caveat here. It's not going to match perfectly because, and no one expects it to, because the model cannot represent absolute reality. There are things going on in these stars that we just aren't modeling. And so those are going to affect the observed light curve, but are going to be neglected in the modeled light curve. So the two of them are not going to match. Plus the fact that you have error in your observational data. So these are the two things that you have to consider when you're looking at the match, the similarity between these two light curves. And ultimately, it lends to the question of how well can you trust the model which you're producing, which I know is of, well, to anybody, that is a key question. I mean, if the model can't be trusted, then it's worthless. So when a scientist or when an astronomer does their experiment, or when they do their analyses, they have to be very specific. They have to be very meticulous as to how they determine the confidence of their result. And so they will often talk about what their model can do, and more importantly, what their model can't do. And they will also talk about the the error analysis or error propagation of their observations. How well can the observations themselves be trusted? Taking both of those two things into account, you then can tell your reader, the temperature of this star, of the primary component, I know that temperature plus or minus 3, it's 5,000 Kelvin plus or minus 250. I know the temperature of that star to within plus or minus 250 Kelvin, or similar. So all data that you extract, or all data that you model, all your results have error bars. If you read a paper, scientific paper, and you see a number that either does not have, if you see a number that is a result that does not have units and does not have an error bar associated with it, that number is meaningless. And you will never see that because, if you do see that, not only is it meaningless, but the journal from which the paper is in is worthless. Because in a refereed paper, in a rigorous paper, that is never going to get through the review process. A reviewer is going to be like, what is this number? What is its unit? What are the errors? Because those are the two vital pieces of information to any scientific data. Is what is it describing, hence unit, and how well can I trust it, hence error bars. All right. So, this is my data. Yay! This is the base, the gross, or the raw data. That's the word I was looking for. And so, yeah. So now let's talk about the actual program that you're seeing me use on this on the screen. This is something called AppJ, or Astro Image J. And depending on what tier of a patron you are for me, I will teach you in depth how to use this with one-on-one instruction if you were wanting to do this. Astro Image J is a free program. It's a free photometric analysis program that can be run on any operating system, any of the big three. Linux, any Linux distro, Windows and Mac. So what do I need to do with this image? Well, I need to do two things to this image. I need to calibrate it, and I need to extract data from that calibrated image. Now, just in terms of time, I'm going to refer to the previous two streams to where I talk about the various different calibration frames that I take. There is the bias frame, there is a dark frame, and there is a flat frame. Each of these removes a artifact, as it were, from the raw science image. So once those are properly calibrated, what I'm looking at is just the light coming from the sky and the stars. There are no more. The light is no longer affected by instrumentation like camera noise or inconsistencies of the pixels or anything of that nature. At least in theory. So hopefully I have done this. Go away. Hopefully I've calibrated all that. I've done that so far. Hopefully these are all my calibrated images. Let me double check. Oh wow, that looks like poop. And I think it has been yes, it has definitely been calibrated. Yep. Okay. All right, Phil, I understand you are on the opposite side of the world. Hopefully you get some sleep, and hopefully your interactions with your students go well tomorrow. So, this is my calibrated image. Oh, we have Little Professor. Awesome. Hi, Little Professor. I don't think I've seen you on my channel before. So, yeah, actually, hold on. Something's weird. Ah, there we go. Okay. All right, so let's first look at this image and say what's going on. Because if you remember, this is what the unprocessed image looked like. Nice and flat. Stars, so forth and so on. Looks kind of like a picture of the night sky. This looks worse, actually. You've got this weird structure here. Now, what I suspect is happening is, and I'd have to go into the calibration frames to be sure, which is something I will probably do offline because that takes a while and is kind of tedious. But for now, I'm going to say, all right, I'm just going to accept that for now. Now, if I do end up accepting this, if I do realize that by not calibrating, I actually get worse data than calibrating it, if I do that, this is something that I have to point out in my paper. That there is a weird sort of brightness gradient in this image, and more importantly, I need to characterize it in some way so that I can Add that the weirdness here, or this gradient. This gradient is going to cause error. It's going to cause distrust in the measurements that I extract. So what I need to do is I need to be able to characterize this gradient to find out just how much it's going to affect my observations. Just how much error is it going to put into it. So, looks a little funky. All right. The other thing that I did, and this is something that I had to that was bugging me the last time, or really kind of stopped me from doing it the last time, was that extracting the data was becoming something of a headache. Because, again, something that I would have done if I had known better, is that the telescope, the DFM telescope, for whatever reason, I said before the DFM telescope was awesome. It is. The issue that we were having at the time was that our tracking was fucking horrible. This thing did not track well at all, at least from a professional standpoint. And so as I took these images, these stars proceeded to walk over to the right, and to the point that I had to actually reposition the telescope in order to get those stars back really into frame. From a data analysis standpoint, for an an AIJ perspective, it really doesn't want to automatically extract data with those big jumps. It doesn't know what to do with them. So I had to figure out a way to tell it the absolute positions of the stars of interest, particularly these 4 stars of interest, and so that I could actually extract the data. And I had to do that by using an astrometric program. Basically, I had to find a plate scale. What it did was it took this image, it then compared it to a catalog of the night sky, and it literally matched up the star pattern to the night sky, and it then said, you're looking here. And then it came back and told me, you're looking at an RA of 6 hours yada yada, and a declination of plus 49 yada yada. RA is stellar longitude, dec is stellar latitude. Stars are identified very much like cities on the Earth, through latitude and longitude. So if I did this correctly, if I did all of that correctly, then what I'm hoping I can do is I can put all of this together. Now this is the part that's now we're going to get into kind of the boring part. Oh, first time in wise. Because I'm going to be doing a whole lot of stuff, just moving files around, so it's not going to be overly, it's going to be kind of like watching a red laser go back and forth. So what I'm going to try to do is I'm going to try to compile all of this data into a single folder so that AIJ knows what to do with itself. So, here, let me bring this over here. I can. First time little professor? Welcome. Alright, so what do I want to do here? I want to create a new folder. We'll call that U. New folder. B. New folder. V. I'm then going to go over here. Now all of these I've got the disk space, why not? Yeah, I've got the disk space. Let's just do it that way. Paste. Now, there's a whole lot of data, at least. So yeah, you can see that each one of these files is a half meg in size. So it's actually, I guess it was a half meg camera. I've got close to 160 images that I've taken. And you can see that because this starts off at 1027, there's a lot of trial and error before I even started taking data that I wanted to actually deal with. And hopefully, as we'll see later on, a good chunk of this data is actually kind of worthless because I really pushed the limits as to how much clouds, or how many, what the thickness of clouds was that I could punch through. That was not very well stated. Don't tell anyone I said this, but depending on the science that you want to do, you can actually observe through a light layer of clouds. Now your data is going to suck, so there's that, but you can do it. This process, or this experience, has told me I don't really want to do that anymore, because yeah, it causes headaches. Okay. Calibration. There we go. Paste. So I think I did 27th, now I'm on 28th. If you folks have any questions as to what I'm doing or why and all that kind of good stuff, please let me know. Yeah, see, this data here probably sucks. I don't know. I probably shouldn't keep it or analyze it, but I'm going to anyway until it's proven to me that it sucks. Because yeah, I'm a glutton for punishment. Dun, dun, dun. Copy. Oops. Paste. So as we can see, my entire data run, or data set, is comprised of 621 images from which I will extract data. So essentially I will have, assuming I can extract images or extract data from all of them, I will have 621 data points for the green light curve. I can tell you now that I will not be able to extract data from all of them. So we will see. So what I want to do now is I want to double check a few things. I want to determine, I want to make sure this is where those stars are what I think they are. So you can see, let's try this. All right. This is my star field. This is the star field that I took. This is the vicinity of HL Aurigae. That one right there is actually HL Aurigae right there. And you can see there, big star, there. These two correspond to these two. This one corresponds to that one. I know it may not seem that way, but when you do this for a while, you get really good at pattern recognition. So I can tell you right now, that is, in fact, HL Aurigae. This is HD yada yada yada, which I'll look up. But for now, I'm going to, yes, I'm going to do this. What star is that? Oh, hello. So, the way that the photometry works is, and actually I'm going to write that down. The type of analysis that I'm doing is known as differential photometry. Photometry is, in its basic form, or basic definition, is the extraction of how bright an object is from an image, or really just the measurement of how bright something is. Let's see, HD 43456, or this star is the 43,456th star in the Henry Draper catalog. Very romantic name. Astronomers are great at that. 9.5. V is 8.24 or 42. So when we look at, so we have this. Oops. Cancel. So because I have these data or because I went through and got the, what's the word I'm looking for, astrometric solution, I plate solved and it knows where it is. AIJ has this nice feature that if you click on it, it'll bring up the Simbad page and it'll tell me, yay, this is what this is the information, particularly the brightnesses. That becomes important in a moment, because you might ask yourself, or ask me, Rob, Professor Parks, how do you know what the actual brightness of this thing is? What I'm measuring is ultimately how many counts I received. How many, in an analogous way, how many photons did I receive in the 3 seconds that I kept the shutter open for this camera? How do I turn that into a measurement of brightness? Well, unnamed person asking me, what I can do that two ways. I can either do it through absolute photometry, which is a nightmare, or I can do it differentially. Differential photometry says is that all of the factors that make absolute photometry a nightmare, such as how much atmosphere you're looking through, the color differences between two various stars, things of that nature, all of that cancels out when you do this particular method. What I'm going to do is, and I can just kill this. What I'm going to do is I'm going to compare my target, HL Aurigae, to a comparison star, in this case HD 43456. I didn't realize it went 3, 4, 5, 6. Anyway, that is my comparison star. And what I'm going to do is I'm going to be comparing the brightness, essentially the number of counts, the number of photons I received from this star, to the number of photons that I received from that star. And there's a simple relationship to that. And the equation for that is the magnitude, if we call this target, this companion, then the magnitude of the target minus the magnitude of the companion is equal to negative 2.5 times the logarithm of the number of counts of the target star divided by the number of counts of the companion star. So I can extract the number of photons from the target star, and I can extract the number of photons from the companion star using this program. From Sinbad, I can then figure out what the apparent magnitude is of the companion. So now of the 4 variables in that equation, I know 3 of them. I can solve for the 4th. Well, rather, Aij can solve for the 4th. And that's what's going to happen in a moment. So, what do I do now? So, what I'm going to do is I'm going to, yeah, that'll work. I'm going to tell it where my files are. Oh, there we go. Select. We're not going, that has already been done. And I'm going to do multi-aperture photometry. I'm going to do this. And let's change the aperture settings. All right. This is getting into the weeds, but maybe one of my students are going to watch this. So, in order to extract the data, basically the counts from this, we have to place what is known as an aperture. An aperture is just, it tells the program, all right, this is the area from which I want you to extract the number of photons received. If it's a simple way, which I don't recommend, then you would do just a simple circle, essentially, and just plop it down on top of the star, very much like you see over here in these yellow circles. If this were the aperture, then the program would extract all of the photons or all of the counts within that circle. And it would say, all right, these are the counts. But a little bit more sophisticated way of doing this is you have to also account for for the sky itself. So if you just looked at the number of counts within this circle, what you would get is you are measuring the amount of light coming from the star, but also the amount of light coming from the background sky. The sky itself has a brightness associated with it. It's not completely black. It does have a certain glow to it, as observed from the Earth. And you want to get rid of that, because you're only interested in the counts coming from the star itself. So the way that we do this is, the way that we get rid of the sky measurement, is we set something, an aperture down that looks like a bullseye, where you have a central disk, which again extracts the star and sky data. And then you have this annulus, I don't know why I'm miming because you can't see me, this annulus or ring around around that central disk. And that annulus, you would extract the number of photons from that, and that tells you how bright the sky is. So you have an inner radius of that annulus, and you have an outer radius of that annulus. Now, I want to, let's see, I'm actually going to do variable aperture photometry. And I'm going to do 0. There we go. So what this is doing is, there is something called seeing. You probably didn't realize this was as complicated as it is, but this is how the sausage is made. So, when you look at an object in the sky, what you're going to see is, obviously these stars are so far away that if you were out in space, they are technically or mathematically represented by a point source. They are so small, so unresolved, that they basically look like a point. Now, when the light from that point source gets to the camera, there are two things that are going to happen to it. One, the light is going to pass through, it's probably easiest to think of it this way, the light is going to pass through a circular aperture, and then that is going to cause diffraction. And that causes the point source, that point of light, to balloon out to a sphere, or to a disk, known as an Airy disk. There's also some wings to it, but if you Google what an Airy disk looks like, you can see what I'm talking about. It's an interference pattern in a sense. No, backing that up, it's not an interference pattern. It's a diffraction pattern. So the telescope itself is going to broaden out that disk. It's going to broaden out that star. On top of that, you have the fact that the light is passing through the atmosphere. Now, the atmosphere, I like to think of the atmosphere as being composed of these little tiny mirrors. And the light from the star, light coming from space, goes through hits the atmosphere, and it plinkos its way down. And what that does is it causes the star to look like it's twinkling. It causes the star to look like it's bouncing around the night sky in a very, very slow, little, small, localized area. When you expose a camera to that for 3 seconds, it's going to expose that, it's going to see that star bouncing around over a small, discrete little area. So the diffraction effect and the seeing effect cause the star to go from a point, basically a single pixel in size, to a disk, like you see here. So these stars that are on this image are not resolved. This is not an image of the star itself. This is not this star is not, say, 3 times as big as that star in radius. All of these stars are still point sources. The sizes that they appear on the camera is simply an effect of diffraction and seeing. When I put down an aperture, when I'm extracting this data, what I need to do is I want to be able to, I want to just get the data from the star as precisely as possible. Basically, I want to eliminate the possibility of any background interference, any sort of noise that the background sky causes. And so what I'm going to do is the program is going to ultimately look at that disk, and it's going to create a profile of what the light distribution looks like, and it's going to optimally put an aperture down to only get the data from the star itself, the star and the light itself. So the background, so for example, the aperture, if you were to look here, there's a lot of wasted space here. There's a lot of ways that the data could be noise from the data, or a lot of opportunity for noise to seep into the measurement. So what this is, if this were going to run this aperture would actually get very, very tight around this small white dot, or what the star appears to look like. I'm going to use variable aperture, meaning that it's going to analyze these stars, or the sizes of these stars, in every frame, because while diffraction is constant throughout, the blurring or the broadening due to diffraction is constant throughout. The broadening due to seeing is not. As you might expect with twinkling, star moves around, and so moves around rapidly. So the amount of seeing, or the amount of blurring that because of that is time sensitive. And so I am going to tell the computer, analyze these stars and give me the best extraction possible. Prompt to enter. I'm also going to prompt to enter in the reference star's magnitude, absolute magnitude. Well, yes, absolute magnitude, or really, its magnitude. I won't get into absolute. There is not right. It should actually just say apparent, but the reference magnitude. And so that is that MC that I was talking about, magnitude of the companion, in that formula that I mentioned. So I'm going to have it prompt me, and I'm going to hit OK. I'm going to click that, and then I'm going to start. And it should start doing something. Where's my log? Oh, shoot. It's all right. I need to reset this. Oh, hello. Cancel. Don't need it to plate solve. So let's start. All right, I don't know what's going on here. Oh, great. I'm going to have to... Oh. It won't let me cancel this, so I've got to click through all of these error messages, through 570 of them. Oh, wait a minute. Nope. Aha! At least you can see what I mean by... Nope, I guess not. If you look right up here, you can see the star, one of the stars moving as the tracking sucks. Holy crow. Alright, you know what I'm going to do? I'm going to just kill it. Just going to kill the whole thing. If I can. Nope. I can't even do that. Man, this is just annoying as... Oh, there we go. It's annoying as poop. How are y'all? I noticed since Phil left, the chat has been noticeably quiet. So I'm going to assume that I'm talking to myself at this point. Which is fine. Oh, I can hold it down and go. Later today, I will be putting a 103 lecture out. But if you've seen my channel, then I've got a couple of 103 lectures that are going to be that I've already covered it. I don't know if I'm going to put out my second cosmology lecture today. I'm hoping that I can, but we'll see how things go. I is a bit tired. Hi, Chris. Not a problem, Rachel. I would not expect you to follow everything I was saying because you have not had the proper background to do it. But if you would, I would be more than happy to explain it in detail through email or however you'd like to communicate. If you're really curious as to how all of this works. So let me do this again. All right. Fit background to plane. Sure. Okay. Use the following keywords. All right. In the measurement table. Okay. Centroid. What I'm wanting it to do is I'm wanting it to only extract data from. Oh, hi, Rodman. How to read JWT data. Yeah, this is kind of what JWST does, although JWST also does spectroscopy, which this is not it. But yeah, it'll definitely be able to, when it comes to exoplanet light curves, if you follow along with this, you definitely will have a better chance of understanding what they're talking about. But what I'm trying to do here is I want to make sure that there's a flip that I want to, there's a switch that I want to flip, that it only looks at data, it only extracts data from images that have been properly plate solved, that it knows where the stars are located in the frame. I think that's fine. How about more settings? La 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 la. Oh, yes, okay. La, la, la. Select aperture. Da, 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 da. Let's do sky annulus as well. Roundness, orientation angle. I don't care about that. Source error, source signal to noise. I don't care about pixels. I don't care about pixels. Da, 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 da. Source mean. Yeah. Sky, and we're gonna do, yeah. All right, I thought I could kill more of that, but because that's gonna be a data file on this is just friggin' ginormous, or the measurement file. I don't need X and Y. I don't need fits chords. Do you kind of want to know that? Moment widths. I'm going to say no on that. Source mean. Yes, I want that. Nope, nope. Oh, I see what's going on there, I think. I don't need that. I don't need that. All right, that makes sense. Hey, Demon Orb. All right. Hopefully this doesn't go too far astray. All right. Auto blah blah blah. Yep. Use RA deck. To locate aperture positions, use single step mode. Nope. Allow aperture changes between slices. Comparison stars. Yada yada. Use previous apertures. Nope. Hopefully it will skip. I'm really hoping it skips and just doesn't break if it can't find the RA deck. If it can't find the stars, then yeah. If not, then I'm going to have to remove stars from background. Assume background is a plane. We'll go with that. All right. Place apertures. Okay. I have a lot of images open that I don't think I want. There's that one. There's that one. And there's that one. Alright, this one I can kill. That I think I can kill. So, left click for target star. Yeah, that's my target. Hey! No comparison found that met the brightness thresholds. Check the brightness thresholds. Oh, interesting. Okay. This is new. Let's do it with continual manual. And that is my comparison. Go away. Ask for you. And the comparison has a magnitude of 8.42. Oh, there we go. That is my comparison. Now, I need check star. Now, the reason why I need check stars is because if I just looked at these two stars, now, if I looked at these two stars and I found that the light varied for T1, I could not be certain. I could not say that the light variation was because T1 was varying, or because the target was varying, or because the companion was varying. In this analysis, I am going to, when I tell it that the magnitude is 8.42, it's essentially setting that for the comparison star. So the comparison star might vary up and down, but make sure this is not actually doing, okay. Might vary up and down, but I'm literally setting it to the magnitude to be 8.42. So I can't trust, where was I going with this? I can't trust that the variability is solely due to the target. So I need what are known as check stars. And so what I'm going to do is I'm going to choose this one. And I'm just going to click OK. And I'm going to choose this one. That's going to be my fourth one. And the check stars, what they do is that AIJ is going to compare the brightness of the target to each of those three stars, each of those three comparison stars. And so when I get the data at the end, when I look at these light curves, I'm going to look at the variance of each of these comparisons. And if any of the comparisons show any kind of variability in and upon themselves, then I'm going to remove them, because that's going to artificially bias my data, my final data. So I will remove them, and then I will redo the analysis and go from there. So what I want all three of these check stars, or the comparison and the choose check stars, to be boring. I want them to not vary one iota. I want them to be constant brightness throughout. So hopefully, and I have done this before, so I'm pretty confident they are constant. Hopefully they are constant, and they can be used to basically gauge just how the brightness varies for the target. And all right, I think I hit enter. Bam! Ha ha ha! Where is it? And it goes! It's the exciting part. Oh wow, it couldn't find any of those. Wow. Well, that data was useless. Oh, that was a good night. That was not a good night. Pop this up. So yeah, I'm definitely going to have to characterize the how flat these stars or these frames actually are. I wonder just how much data I'm actually going to get out of the 600 and some odd frames that I got. How many of them am I going to get? Let's see. Let's see. My passion for music limits my time for other things, sadly. Hey, you got a passion. That is a rare thing in my opinion, or a rare thing in my experience. Passion should be treasured. All right. So, what do we got here? This is a little hard to see, I grant you, because it's two different. If it's multiple days, all plotted at once. But hopefully, like right here. Actually, I have power. Let me do this. What I can do is I can change the scale so that we can zoom in on. Actually, can I do? No. I can change the scale. Let's see here. Let's do. I want to do x-axis scaling, so let's do 1.5 to actually auto range. There we go. Let's do all right. Max to minimum. All right, minimum is 3, so let's go to 3 days past. Go. All right, better. So I'm just zooming in on a certain subsection of data. All right. Something is looking weird with this, I will grant you, and I need to figure out something. But just as a, what's the word I'm looking for? Sanity check. What I can see is that this star is definitively varying. It dropped, it went back up, it dropped, it seems to go back up. This is not the shape that I would expect for this particular type of variable star. So something is weird here. And the other thing, what I'm also seeing is relative flux normalized. What I want is delta magnitudes. I told it what the magnitude of the reference was. So I need to figure out why it's giving me in flux. Also, what's not plotted here are my other stars. So, like the comparison stars, so that I can check to see whether or not those are in fact variable. So let's go over here, and I can do this. I have T1, I have that, boom, and boom. Shoot. All right. Now the plot is really complicated. Really, I've got data all over itself. So what I want to do is I need to separate this out somehow. So I am going to shift these. Shoot. All right. What? Why do I want it? Why is it scaling it so badly? To select arbitrary scale, click on. Select to arbitrary plot scale and shift by percentage of the white plot data. Multiply by this factor. Deselected. How about that? I suppose that is possible, that there is in fact a Death Star blowing up somewhere. I would hope not. Oh, wait a minute. I know what I'm doing. All right. That needs to be 1. That needs to be 1. That needs to be 1. Don't know why this is all fudged. Now, this is 0.5. What I'm doing is I'm shifting these, shifting this data so that it's is easier to look at. So, all of these are not. All of these are. Nope, that's not what I wanted to do. All right. Dun dun dun. Well, that's all right. That's bizarre. So, I will need to zoom in on these, but you can see that the comparison stars are pink, salmon, and red. And like I said, I wanted these stars to be stable. I wanted these stars to be constant. And so, what we can see just the first order, yep, these stars are definitely constant with respect to these really variable stars, or the really variable star. But just to make sure, I will zoom in on them. All right, custom range. We'll go from 1.4 to 1.2. Custom range. All right, even less. So 1.29. That's max. 1.31 to 1.29. Well, that didn't work. That's not the right. What? I don't know why this is being annoying. 1.4. Four, 0.8. Okay. I've got a pen in my mouth. That's why I'm talking like this. Wow. So yeah, real stable. There's something there that I need to that I will need to play with. I'm going to do that offline at some other point, or sometime this week, and I will come back to that, and I will tell everyone. Hey, Indie Tiger. I am going to what's the word I'm looking for? Summarize what I did offline on the next stream. But before I go today, what I want to do, I'm going to replot that. Boom. All right. What I want to do is get this into relative magnitudes. Bum, bum, bum. And so I think if I do this, and then do that. All right. Yep. Well, that didn't work. Yeah, that sure as shit didn't work. Let's see if I can just redraw that. Oh, what am I doing? I want to do that, but I want to do that. All right. Here we go. Relative flux, source error. Boom. There we go. Now we're cooking with gas. Source magnitude for 2. Source magnitude for 3. Whoop. Source magnitude for 3. Source magnitude for 4. There we go. Auto error. Okay. Shoot. So now, what I'm looking at here, and actually I want to flip this around. I think delta magnitude. This is the delta mag. So what this is telling me is delta mag. This is source minus comparison. If it's positive, I hate the fact that these are switched, because I always have to think about this. If the number is positive, then, or the number gets larger, that means the target is the target magnitude is larger, the number is larger, therefore it's getting dimmer. So I need to flip this. Now, how do I flip it? Can I do that? Can I flip it easily? Probably not. Oh, yes, I can. And 1.8. I don't know. Like that. So now I can look in. See. 6.5. All right. So what does this mean? What am I looking at here? What I'm looking at, again, something's funky is going on with this data, so I'm going to need to look at it a little bit more in depth to figure out what's going on. What I've done is I've added the error bars to the data, first off. So that basically tells me how well I can trust each individual data point. What we're looking at is delta magnitude, and by delta magnitude, what delta magnitude is the target minus the comparison. So, why is that? It's normalized. All right. I was like, why is that 1? It shouldn't be 1. Oh, there we go. Off. 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 There, wow, okay. Maybe I do need to normalize them. Oh, how about not? Oh, shoot, come on, stop doing that. Something weird. AIJ. See, what should happen, what should be going on here is the comparison star should be set to 0 because it's basically it's the delta mag of itself. Since I've set it to 8.42 and it's set there, then there should be no, by default, there should be no variation. So the delta mag should be 0, but it's not. So I'm going to need to look into why this is plotting it this way. This is the first time I've really used this program for this particular data set. So, yeah, I'm wondering why this is doing its thing. This is a function of, okay, so this is a function of the delta mag of T1. So why is the delta mag of T1 close to 0? That doesn't make any sense. Let's do negative 0.001, negative 0.001. There we go. Hey, that looks better. Let's do 0. That looks even better. I don't know where this variation is too small, because I'm definitely not seeing near the micro variability, micro mag variability. So yeah, but that's basically in principle what it should look like. I really wish I was ending on something that was a little bit more cohesive or a little bit more convincing. But let me see if I can get this. Let's go back to the typical way of expressing this. Look by relative fluxes. Relative flux, that's the error. Come on, where are you? Doop. Relative flux. Relative flux. Come on, where are you? There we go. Let's plot that. What the hell is up with pink? Oh, that's right. There we go. That actually makes sense because relative flux is 0. So, oh wow, this is interesting. This is set to 0. So something is going on. Since all of this should be 0, something else, there's a systematic error going on with this particular data set. Oh, I should probably do this first. So this data set looks good. This data set looks good. This data set, there's some funkiness going on there that I need to look into. Here, there's a little bit of funkiness going on there. And yes, those are technical terms. So while we have that, let's actually look at, let's see, let's do this. Let's zoom in on that data. And let's take that off. So yeah, that's dead on 0. That's pretty much, that's what I want to see right there. Let's stop plotting it. And then auto. So we have this kind of light curve. It does that. There is a little bit of variability in T3 or into the in the comparisons, which I'm not real happy with. There's a lot of noise in C4. So, yeah, there's a lot to do with this. Moral of the story right now, and I am going to transition. So I'm about to end it here, end the stream here. And I'm going to fiddle with this sometime over the week, and then same bat time, same bat channel. Next weekend I will come back. But one of the lessons I want folks to get out of this experiment, and what I mean by experiment is this stream, is I want folks to see just what all goes into data analysis, not just the astronomical or the physics of it, but the literal trial and error, the way that data is analyzed. Like I was saying before, with this we have, this is basically first blush. This is what I'm just doing the first run through of this data, and I'm seeing some things that are worrying me. Obviously there is, obviously there is this stuff that I need to worry about. I really wish there was a way that, oh, what the hell? Okay. I don't know what's going on here, what's causing this, but obviously something is going on with this data set which is going to be affecting that. Some throwing in systematic errors. So I need to look at those images and figure out what it is that's causing them. And then on top of that, I'm definitely seeing some correlated error. When I see that the comparisons are doing the exact same thing as the target, that bothers me. The comparisons shouldn't be doing anything. They should just be flat. So yeah, kind of like what's going on up here, and kind of what's going on up here. So again, returning to the point that I'm trying to make in a very long-winded sort of way, is through the first blush, when you do an experiment, particularly in astronomy, when you're doing something like when you're extracting data, you're never going to get it right the first time. There's always going to be some kind of error or systematic problem in the data that you need to deal with. And what I want to do is over the week, I want to return to this, and I want to return to this, and I want to basically find out what is going on, and then be able to let folks know what's going on and what to look for when doing this type of analysis in the future. But the sad truth of it is, when doing observational astronomy, is you're going to be running your data over and over and over and over again until things pan out. This is not to say that I am fudging the data. This is not saying that I'm manipulating the data or massaging the data, as we like to call it. What I'm saying is that there are going to be errors. In this case, I'm sure there are frames of data where the error involved is crap. And so I will just need to exclude that data from my analysis. There's also data that I think is good that it's not included in the analysis, so I'll need to figure that out as well. But basically what I'm trying to say is, if you're going to do this work, you expect to have to rerun data analysis over and over again, because there's always going to be something that you missed. There's always going to be something you didn't take into account, and hopefully you're going to see that in your data. In the extracted data, and then figure out what the problem is, and then go back for it, and then fix it, and then reanalyze stuff. So, all right, thank you all for sticking around and watching this, and I hope to see you all next Saturday. Oh no, I'm sorry. Next Saturday, I'm going to be talking about the Artemis mission. Hopefully on Monday morning, the Artemis 1 will launch, weather permitting. I think if it doesn't, the next launch window is in October, but I could be very wrong about that. It's definitely months off. If we don't get it tomorrow, then it's going to be a few months before the launch window opens back up again. But yeah, so next Saturday morning science, I will be talking about the Artemis mission. And then after that, I will be revisiting the HL Aurigae data. So, all right. Are there any questions that I can answer before I get off here, or we sign off? Rodman, the application I'm using is called Astro Image J. I'm going to type that in the Astro Image J. Actually, let me see if I can do this for you. This is a very powerful tool. Oh, you couldn't see that. Let's go back to this. This is the website. I'll post that link in the chat in a second. Paste. There's the link. This is a very powerful data extraction program for CCD images. I'm barely touching the surface of this. There is still plenty more exciting data analysis to go through. I need to check out essentially if there's any correlations with air mass. I need to check out what the errors are. I have it posted in your Discord. Oh, sweet. Yeah, I posted them at Discord if it's not there. So yeah, very powerful program. It does have somewhat of a steep learning curve to it, as hopefully you can see. Even I sometimes wonder what the hell it's trying to do. But it runs on any operating system, like I said, any distro of Linux, any Windows box, any Mac box. It gets a little flaky. On paper, the different operating systems shouldn't matter, but I've actually found that AIJ does not like Mac more than it doesn't like Linux and Windows. It seems to run best on Linux, then best on Windows, and then worse on Macs, to the point that Macs are kind of a headache. Clive, how do these sorts of observations help to develop the science of astrology? You mean like Aries? They don't. They do a great job of proving that astrology isn't a science. For a couple of reasons. Pisces, actually, Chris, you're probably not a Pisces. In reality, the news seems to get a hold of this every so often, like they seem to have forgotten that they've actually talked about this. One of the reasons why astrology don't work is because of something called precession. And what precession means is that the Earth, not only does it rotate around an axis, but that axis also rotates across the sky. So right now, Polaris is the North Star. But actually, no parking, but actually in about, let me get this right. I always get the time frame wrong. I think the total period is 14,000 years. So in 7,000 years, the North Star will actually be Vega. The period, 14,000 years, seems like a long time. But if you think about it, astrology has been around for about 2,000, 3,000 years. So it's definitely been long enough that precession has affected where things are located. So the way the signs are, as far as I know, the way that your astrological sign is determined is what constellation the sun was when you were born. So when it says that you were a Pisces, that means that the sun was supposed to be in the constellation of Pisces when you were born, but in actual fact, you're probably one off. I am technically an Aries. Or I am an Aries, but I think I'm technically a Pisces. Do you need to know how to do this analysis on paper before you can do it with this program? It helps. To know how to do what I mean by do the analysis on paper, what I really mean is just knowing the fundamental understanding of what delta magnitudes are, how to extract the data, like what are counts, how do counts relate to magnitudes, that sort of thing. But yeah, so with the program, you do need, in order to use the program, you really do need a working knowledge of the field of photometry, of dealing with photometric data. But here we go. Let's look. So just so you know, the other reason why astrology ain't a thing is because there are actually 13 zodiacal signs, not 12. Recession. Why is your zodiac sign probably wrong? Give me a chart. Give me a chart. Mm-hmm. Mm-hmm. No. Yeah, okay, so these are the right ones. These are the actual corrected ones, I think. March. Yeah. I'm March 26th, so I am technically a Pisces. For some reason, they don't have Ophiuchus in here, which is an error. Ophiuchus is the 13th zodiacal sign. Oh, there we go. Scorpio is combined here with the constellation of Ophiuchus, through which the sun passes between November 30th and December 17th. So if your birthday happens to be between November 30th and December 17th, congratulations, you are an Ophiuchian. So, let me see. So, Chris, you are an Aquarius. Hey, all right. So, yeah, typically, obviously there are cusps and things of that nature, but if you know your astrological sign is probably the sign, the next sign over. So, Aries turns into Pisces, Pisces turns into Aquarius, Aquarius turns into Capricorn, blah, 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 blah. And yes, it's all full of crap. Astrology is the ultimate pseudoscience. All right, folks. Again, thank you for sticking around and watching this with me and going through this with me. I very much appreciate it. If you like this sort of content, please like, share, and subscribe. Also, I'm going to, as much as it makes me uncomfortable, I'm going to plug my Patreon. The Patreon, if you want to help support the channel, and what I mean by support the channel is that by supporting me, you are going to be supporting public outreach of George Mason University, primarily through our student organization, so that we can bring astronomy to underserved communities. Either schools that do not have the funding to provide telescopes or astronomy content in their curricula, or just rural areas that just do not have the don't have the resources for it. Basically, and whatever reason they don't have the resources, we want to get in contact with these folks, and we want to reach out to them and bring astronomy to them. So if you want, if you would like to help support me in doing that, please consider becoming one of my Patreons. All proceeds from my Patreon go to the student organization and George Mason. I don't keep any of it. All of that money goes to helping with outreach. So, that being said, thank you again. Tomorrow I am going to be, I probably should have mentioned this when Blue was on. Tomorrow I have Coffee and Science at 10 a.m. Eastern Standard, or Daylight, or whatever the hell we're in. And it's going to be a little different, because this time I am not going to be talking to a professional scientist. I'm going to be talking to a flat earther. I'm going to be talking to, assuming that he's still up for it, I'm going to be talking to Dan the Waterman. And we're going to be talking about, what I'm hoping that we can talk about is why he distrusts the accepted science, for lack of a better word. And he also seems to have a problem with the flat earth community. He does not believe that the flat earth community is as organized as it should be, and there's too much infighting and too many cliques within it. I don't want to speak too much for him, but that's the impression that I got, so we're going to be talking about that as well. What are his motivations for being a flat earther, and what he believes the flat earth movement needs in order to move forward. So, I think it would be very informative to folks on both sides of this issue, as it were. So I hope so too, Chris. I hope that he's easier to talk to than Sleepy. Although, Sleeping Warrior was Anthony was good to talk to. Like, he was easy to talk to. He wasn't an asshole, basically. Well, at the end, maybe so, but for the most part, he was very civil. It was a good conversation, I thought. But I've talked with Dan, and he and I have both said that we want a cordial conversation. We don't want to, as he puts it, he doesn't want the gloves to come on and have us box, although he's willing to if need be. This is meant to be just a conversation. Just, I want to know more about what he believes and why. And like I said, I'm also very curious as to where he thinks Flat Earth should go, where he thinks the community should head. Okay, I'm going to sign off. Thank you all for. Yes, you're Stevie B. You are very right, and I'm going to be. Looking into that. I do have a few mods. They weren't on today, but I will be making sure that some folks that I trust will become mods if I can figure out how to do that. Just to be on the safe side, because I don't know. I'm actually hoping that Dan will advertise this to the Flat Earth community, and that we'll actually have Flat Earthers, or I guess what they're now known as globe skeptics, on, so that we can actually have a polite conversation, both between Dan and I and folks in the chat. So hopefully, Rachel, you'll be there, because I would be curious as to know your thoughts on what Dan has to say. All right, folks, it's been a pleasure. I'll see you. Hopefully, I'll see you tomorrow. If not, I'll see you next time. Peace out. Clear skies.